This video covers the limit definition of a derivative, or the alternate form where you can find the derivative at a particular x value. If you haven't watched my video, Exploration, Slope of the Tangent Line, I encourage you to go back to see where does this formula even come from. How did we get the formula for a derivative, also known as the slope of the tangent line? Now that we have the formula for finding a derivative, let's use this. It's called the limit definition of a derivative. Let's use this formula to find the following. d over dx of x squared is asking you to derive with respect to x, whatever function is inside, or directly after the d over dx. The function we want to derive is x squared, so f of x plus delta x would just be replacing the x with x plus delta x, and then squaring that quantity. Let's plug it in. At this point, we're just going to do algebra. So expand, then combine like terms. Now I notice that each of these terms has a delta x, so I will factor out delta x in order to be able to reduce it, and then we'll be able to direct substitute. At the time of direct substitution, you do not put that limit notation any longer. And what were we finding? d over dx of x squared. There's our derivative. Because number 2 is asking for a specific derivative, f prime of 1, we're going to use the alternate form. A is the number for which you're trying to find the derivative. So in this case, A is 1 because we want to find f prime of 1. What is f of A, or f of 1? That just happens when we plug in 1. F of 1 is 1. The limit as x approaches A, which is 1, of f of x cubed, minus f of a, 1, over x minus a, which is 1. You may notice that, we can factor x cubed minus 1. It is difference of perfect cubes. And now it's possible to use direct substitution. So f prime of 1 is 3. Y is equal to 1 over x, and so we're going to find y prime, the derivative. My function is 1 over x. So f of x plus delta x is going to equal 1 over, and we just replace the x with x plus delta x. And we'll evaluate with the limit definition of the derivative formula. When you're evaluating the limit of a complex fraction, your first step is to get a common denominator so you can combine those fractions. We have common denominators on the top two fractions, so we can combine them. This negative sign distributes to both pieces of this numerator, so minus x minus delta x, all over x times x plus delta x, all over delta x. When you're dividing a fraction by delta x, you're just multiplying that fraction by 1 over delta x. So we can reduce our delta x's. And finally, direct substitute. Y prime equals negative 1 over x squared. Find the slope of the tangent line at x equals 1. Slope of the tangent line is the same as derivative. So we want to find a particular derivative. The one at x equals 1, we can use the alternate form of the limit definition of a derivative. A would be 1, the number we're approaching. F of a would be 1 over 1 squared. As x approaches a of f of x, which is our function, minus f of a, or f of 1, all over x minus a. When you're evaluating a limit of a complex fraction, combine those fractions. At this point, we've run into a slight problem because it looks like we cannot reduce anything, and yeah, that would make direct substitution impossible. So what do? There is a little factoring maneuver we can do. This right here is negative x squared plus 1. And if I factored out a negative, I'd have x squared minus 1, which is the difference of perfect squares and will reduce with this x minus 1 in the denominator. Now we can direct substitute. And that is y prime at 1. Find f prime of 2 for this f of x, then write the equation of the tangent line at x equals 2. Because they're asking me for a specific derivative, I'm going to use the alternate form of the derivative. A is equal to 2, and f of a is 25. So the limit as x approaches a of f of x minus f of a over x minus a. Again, it may look like nothing's going to reduce, so let's try factoring the numerator. So 13 and 2 make 26. We want the 13 to be positive and the 10 to be negative. This one's going to reduce, and then we'll be able to use direct substitution. F prime of 2 is 23. That is the slope of the tangent line. So now to find the equation of the tangent line, we need a point and a slope. Do we have the point at x equals 2? Yes. When you plug in 2, you get out 25. Therefore, our equation is y minus y1 equals slope times x minus x1. They're asking for a general derivative and then a specific derivative. When you're evaluating the limit with radicals, then you need to multiply by the conjugate. Rationalize the numerator. And at this point, we can direct substitute. Which is 1 over 2 root x. And if we're finding f prime of 4 as well, we don't need to use the alternate form of the limit definition of a derivative because we actually have the definition of the derivative right here, and we can just plug it in. So f prime of 4 would be 1/4.